Hello. In the previous couple of videos, we were building a theory based on the cramers rule, and we have proved in the previous videos that the inverse of A is equal to adjoint of A over determinant of A, and we have also explained how to find the adjoint of a given matrix and how to find the determinant of the given matrix. So once you know about the inverse of A by using adjoint method, then you can explain what is Cramer's rule. Suppose you have a given system of equation. So for any system of equations, we can write a matrix form. So the matrix form of any system of equation can be written as, linear equations can be written as a matrix A, a coefficient matrix A times the variable matrix X times equals the constant matrix B. Okay, we will deal everything for 3 by 3 matrices. So for example, if I have system of 3 linear equations with 3 variables, for example, a11x1, a12x2, a13x3 is equal to b1, and a21x1, a22x2, a23x3 is equal to b2, and a31x1, a32x2, a33x3 is equal to b3. For example, if this is the system of linear equations, then this system can be written as the product of matrices equal to a constant matrix. So this product of matrices corresponds to this system, and this constant matrix corresponds to this column matrix. Okay, so how can we write it? Here A is equal to the coefficient matrices elements a11, a12, a13, a21, a22, a23, a31, a32, and a33. Here A is this matrix, these elements, the coefficients of the linear equation, and the second row is the coefficient of the second equation, and the third row is the coefficient of the third equation. Okay, and similarly here X is the variable, the column vector matrix determined by the variables. The variables are x1, x2, and x3, and constant matrix B is this matrix. I can write B1, B2, and B3. Using these 3 matrices, we can always write the system of linear equations in this matrix form. Okay, so if we have a lot of equations, our rows will get increased. If we have a lot of variables, I have only 3 variables, our column will get increased. Okay, so we are just considering 3 by 3 system. Okay, so our system is AX is equal to B. So this system has unique solution if and only if the determinant of A is not equal to 0. Okay, so this system is solvable, or it has a unique solution if and only if the determinant of A is not equal to 0. Okay, so if the determinant is not equal to 0, then we can shift this matrix A to the right side of an equation, because we have to solve this system. In order to solve this system, we have to find the value of X, In order to find the value of x, we need to shift a to the right hand side of the equation. How can we shift this matrix A to the right hand side? If they were the numbers, then I could just divide by A on both sides, but I can't do that because they are not numbers, they are matrices. So we cannot divide by matrices. What can I do? For matrices, I can multiply by the inverse of a matrix. In other words, what can I do? If I have to take this element to the right hand side, I will shift A here, but I will write its inverse, right? So I can write x is equal to A inverse of B rather than writing B over A, because B over A cannot be done. Okay, generally what you do in the algebra, you do x is equal to B over A, but here B over A will not work because they are matrices. Here you will write x is equal to A inverse of B. Instead of division of A, we will write A inverse, okay? And since we know that A inverse is equal to adjoint of A over determinant of A, so I can put this value here. My x will become adjoint of A over determinant of A. This is A inverse, and then I will write B here. So my x is equal to the product of these two matrices, okay? And remember, what is adjoint of A? If I have this matrix, if my A is this matrix, then the adjoint of A is what? Here I can write adjoint of A. I am going to just remind you, it is A11, A12, A13, A21, A22, A23, A31, A32, A33. Not, this is just the matrix of cofactors, but adjoint is not just the matrix of cofactor, but its transpose, okay? So the adjoint of a matrix is the transpose of the cofactors, okay? So how can we apply this transpose on these cofactors? I can write this way. A11, A12, A13. Write this row as a first column and then this row as a second column. A21, A22, A23, and then A31, A32, and A33. Actually, this is the adjoint of A. Okay, so we know adjoint of A by the previous videos. So I can put this value here, okay? Okay, since adjoint is this matrix, I can plug this value here. But my x is equal to actually x1, x2, and x3. And then 1 over determinant, I will write 1 over determinant of A. Usually I denote determinant of A by this notation. Okay, you can write determinant of A. If you don't like this notation, you can just write determinant of A. And then I have adjoint times B. What is adjoint of A? Adjoint of A is simply this matrix which we already know from the previous video. So I will write this matrix times matrix B. Okay, 1 over determinant of A times adjoint times B. What is B? B is just the constant matrix, this matrix, okay? So then I will write B here, and then I can solve this system. In order to solve this system, I will multiply these two matrices. So my first two terms will remain the same, this thing and this thing will remain the same. Then I will multiply this with this. I'll multiply this matrix with this matrix, okay? So first of all, I will multiply the first row with the first column, A11, B1. So what is that? B1, A11 plus B2, A21 plus B3, A31. Okay, look, I multiplied this with this. Now I will multiply this with this, and I will go down. B1, A12, B2, A22, B3, A2, A32. Okay, how? Look, B1, A12, B2, A22, B3, A32. Okay, and similarly I will multiply the last row with this column again. So B1, A13, B1, A13, B2, A23, B3, A33. Okay, all right. Now I will find what is x1. x1 is simply 1 over determinant of A times the first row. And similarly, x2 is 1 over determinant times the second row, okay? And x3 is 1 over determinant times the last row. Okay, let me write first x1. x1 is 1 over determinant of A times the first row of a matrix. So the first row of a matrix is this one. So I will write 1 over determinant of A times the first row. Okay. All right. Now, if I write it more in the more details, 1 over A determinant of A is as it is. I can write B1. What is A11? In order to find A11, we will look at the matrix. A11 means the cofactor determined by this number. The cofactor determined by this number is obtained by forgetting about this column and this row. I will get this, the determinant of this number, okay? So I will write the determinant of A22, A23, A32, A33, okay? But don't forget about negative 1 to the power 1 plus 1, since negative 1 to the power 1 plus 1 is plus 1, so I didn't write here minus, okay? Then, okay, I have done with these two things here, okay? B1 as it is, A11 I have written down. Now I will write plus, I will write B2, and then A21. What is A21? A21 is the cofactor determined by this element. So in order to find the cofactor determined by this element, I will forget about this row and this column. But one important thing is that I will also write minus 1 to the power 1 plus 2, which is minus 1. So I will write minus 1 times the matrix of determinant found by these elements, A21, A23, A21, A23, then A31, A33. All right. Then, okay, this minus can be written here in order to simplify our numbers, okay, because plus b2 times minus of the determinant is just minus b2 times the determinant. Okay, and then we have, okay, I have done with these two things also. Now I will do with this b3 times the cofactor determined by I'm so sorry about that. This is not correct. A21 means the cofactor determined by the element in the second row and the first column. This means second row and the first column. So the element in the second row and the first column was this one. Okay. So I will write the determinant of these numbers, right? A12, A13, A32, A33. So I will write A12, A13, A32, A33. Okay. And then I will write B3 times A31 plus B3 times A31 means I will write minus 1 to the power 1 plus 3. So it is plus 1, so I will not write this. A31 means third row and first column. And here third row is this and the first column is this. So the determinant obtained by the submatrix by removing the first column and the last row. So it is A12, A13, A13 and A22, A23. Oh, okay. All right. Now I can simplify these things. If I write this whole thing in a determinant form, I can write in this way. Look at that. This thing becomes very interesting. 1 over determinant of A, and this whole thing is the determinant of this matrix. B1, B2, B3, then A12, A13, A22, A23, A32, A33. Maybe you will not agree with me at this point, but if you expand this determinant along the first column, then you will exactly get these things. Look, so if I expand the determinant along this first column, first I will get B11, okay? Then I will remove this and this, I will get the determinant of this. So B11, so B1 times the determinant of this thing. And you have exactly B1 times the determinant of this thing. Since I am expanding the determinant along the first column, so the next term is B2. If I forget about this column and this row, I will write minus B2 times, because minus 1 to the power 1 plus 2 is minus, B2 times exactly the determinant of these two things, okay, which is here. Then I will go with the next entry of the same column. I will again forget about this row and this column. So B3 times the determinant of this thing. Okay, so that means this whole determinant is equal to this determinant, this whole thing. So look, my x1 is obtained by adding, you know what is this? This is matrix B, okay? So in the first column, we have matrix B, and the other two columns of matrix are the same. Actually, your matrix A was A11, A12, A13, A21, A22, A23, A31, A32, A33. So the way we have found everything is, look at the symmetry. X1 is obtained by dividing, by writing 1 over the determinant of A times this matrix, but replace the first column by the matrix B, okay? If I replace this first column by the matrix B and the other two columns remain the same, then we will exactly get the formula for x1. So this thing I have already proved, okay? So x1 is obtained by writing this thing. By looking at this symmetry, we can find x2 also. So I will not prove for x2, so I will write similarly. X2 is equal to the same thing. X2 is equal to 1 by determinant of A. So I will write 1 by determinant of A times the determinant of this matrix, but last time we replaced this column by matrix B and the other two columns remained the same, but this so because it was x1, but now we are going to find x2. So what will I do? Instead of replacing first column, now I will replace second column by matrix B and these two columns will remain the same, okay? So I will write A11, B1, A13, A21, B2, A23, A31, B3, A33. I have written it directly, but you can prove by comparing this x2 is equal to 1 by determinant times this whole thing. And once you will write this whole thing here instead of this thing, then you will get this kind of formula, which will be exactly this whole determinant, okay? Similarly, you can write x3 is equal to 1 by determinant of A. So in order to find x3, you will replace the last column, the third column, by matrix B, and the first two columns will remain the same. So you can write A11, A12, B1, A21, A22, B2, A31, A32, and B3. This is what called Cramer's rule, okay? This is called the Cramer's rule. Usually this whole determinant is represented by A1. A1 means the matrix obtained by replacing the first column by the matrix B, okay? I mean, this whole matrix is usually named as A1, okay? You can call it A1. So I can write the determinant of A1 over the determinant of A, okay? Similarly, this matrix will be named as A2. Why A2? Because this matrix is obtained by replacing at the second position, the second column by B, okay? That's why it is called A2. So it is the determinant of A2 divided by the determinant of A. And similarly, it is the determinant of A3 divided by the determinant of A. This is called the Cramer's rule. In the next video, we will solve some examples using the Cramer's rule.